Close your eyes and listen to a clock. Imagine it is sitting on a wooden bedside table. Perhaps it is an old analog clock, the kind with a mechanical heart, ticking softly in the quiet of a room. Tick, tock, tick, tock. The sound is steady, rhythmic, and familiar. It is the sound of time passing in a straight line, orderly and predictable. It is the sound of a world that makes sense. As you listen to that steady rhythm, let your breathing match it. Slow down. There is no rush here. The day is done. The noise of the traffic outside has faded. The screens are dark. There is only this room, this moment, and the steady, reassuring beat of the second hand making its way around the circle. Now, let your mind drift outward from that clock. Imagine the room you are in. It is anchored to the floor. The floor is anchored to the foundation of the building. The building is anchored to the earth. Feels solid, doesn't it? Beneath you, the ground feels immovable. If you were to walk outside and stand on a patch of grass or a sidewalk, you would feel the weight of the world pushing up against your feet. It feels like a stage, a permanent, unmoving platform where the drama of your life plays out. But you know, in the quiet back of your mind, that this stillness is an illusion. You know that the ground beneath you is not a stage, but a ship. You are riding on a tremendous sphere of rock and iron, spinning through the dark. You are traveling at speeds that would tear a machine apart, yet everything around you feels perfectly still. The water in a glass on your nightstand does not tremble. The books on the shelf do not slide off. The air in the room moves only with the gentle current of a fan or a draft from the window. The universe is calm, even when it is strange. We call this ship Earth, and we call it a planet. The word planet feels heavy and certain, like a stone you can hold in your hand. When we were children, we learned the names like a nursery rhyme.
Mercury, Venus, Earth, Mars.
Jupiter, Saturn, Uranus, Neptune. And for a long time, Pluto. We saw them in textbooks, painted in bright, distinct colors. The red dust of Mars, the swirling cream and ochre storms of Jupiter, the deep, icy blue of Neptune. They were distinct characters in a story that had been written long before we were born. They were the family of the sun. We grew up with the assumption that we knew what a planet was. A planet is a big round thing that goes around the sun. Seems so simple. It feels like a category that nature created, obvious and undeniable. You look at the sky and you see points of light. Some of them twinkle. Those are stars. Some of them shine with a steady, unwavering light. Those are planets. The ancients saw this difference thousands of years ago. They called them wanderers, planets in Greek, because while the stars moved together like a fixed tapestry, these few bright lights marched to their own rhythm. They wandered across the constellations, independent and free. So, a planet is a wanderer. Planet is a world. Planet is a home. These definitions sat comfortably in our minds. They felt like facts, as solid as the ground beneath your feet. We like categories. We like to know that a chair is a chair, a bird is a bird, and a planet is a planet. It gives us a sense of order. It makes the universe feel tidy, like a well-kept library where every book has its place on the shelf. But tonight, we are going to gently peel back that label. We are going to look at the universe not as we wish it to be, tidy and categorized, but as it actually is. And as we do, we might find that the categories we invented are not as solid as we thought. The universe is messy. It is overflowing with variety. It creates things that defy our simple labels. It creates worlds that are too big to be planets but too small to be stars. It creates rocks that act like worlds and worlds that act like rocks. It creates lonely wanderers drifting in the black void between the stars, tethered to no sun, warming themselves only with their own internal heat. As you lie there, listening to the imaginary clock, consider this: what if the word planet is not a definition of what is out there, but a reflection of how we see ourselves? We live on a planet, so we define the universe in terms of planets. We look for mirrors of our own home, but the cosmos is vast, and it is not obligated to match our expectations. What feels fixed is often only familiar. Let yourself visualize the solar system now. Not the flat diagram in a textbook, but the deep, three-dimensional reality. Imagine the sun, a roaring ball of plasma, holding everything in its gravitational grip. Feel the heat of it, even from 93 million miles away. Now visualize the planets moving around it. See Mercury, scorched and cratered, racing around the sun every 88 days. See Venus, wrapped in thick, crushing clouds of acid, spinning slowly backward. See Earth, blue and white, teeming with life, carrying you and everyone you know. See Mars, a rusted desert world with dust storms that swallow the entire globe. Move further out. Cross the asteroid belt, a river of tumbling rocks. See Jupiter, a colossus of gas, a failed star that never ignited, with storms that have raged for centuries. See Saturn, the jewel, with its impossible rings of ice shimmering in the sunlight. See Uranus and Neptune, the ice giants, cold and distant, guarding the outer edges. And beyond them, what? Darkness? Emptiness? Or something else? For a long time, we thought the story ended there. We thought the solar system was a finished painting. But in the last few decades, we have discovered that the painting is not finished. We have found new colors, new shapes, new shadows. We have looked at the dark edges of the canvas and realized that the frame is much wider than we believed. And in doing so, we have had to ask ourselves a question that seems almost too simple to ask. What is a planet, really? It is a question that sounds like it belongs in a kindergarten classroom, yet it is a question that has torn the astronomical community apart. It is a question that challenges our understanding of history, of language, and of nature itself. It is a question that reveals the beautiful complexity of the cosmos. A planet is both a thing and a question. Tonight, we will walk the line between the solid ground of intuition and the shifting sands of discovery. We will travel from the ancient observatories of Babylon to the modern control rooms of NASA. We will visit worlds made of diamond and worlds where it rains glass. We will meet the astronomers who fought over the definition of a word, and in doing so, changed the way we see the sky. We will drift through the Kuiper Belt, float above the clouds of exoplanets light years away, and stare into the dark specifically to find what we cannot see. But through it all, we will remain calm. We are not here to solve the riddle of the universe tonight. We are here to witness it. We are here to let the vastness of space wrap around us like a heavy blanket. We are here to remember that while our definitions may change, the worlds themselves keep spinning. They do not care what we call them. They simply are. And there is a profound peace in that realization. The clock on the bedside table continues its steady rhythm. Tick, tock, tick, tock. It measures a human second, a human minute. But out there, the planets measure time in orbits that last hundreds of our years. They move with a slow, majestic grace that makes our busy lives seem frantic by comparison. Tonight, we will borrow some of that slowness. We will borrow the patience of geology and the silence of the vacuum. So let go of the day. Let go of the need to be right, the need to categorize, the need to understand everything immediately. Let yourself be a wanderer, just for tonight. Let yourself drift among the spheres. The universe is calm, even when it is strange. We begin our story not in ancient times, but in a moment many of us remember clearly. It was a moment when the orderly list of planets we had memorized, the list that ended comfortably with a ninth name, suddenly felt unstable. It was the moment the universe cracked open, just a little, and showed us that our map was incomplete. The year was 2006. The location was Prague, a city of spires and cobblestones, ancient bridges and astronomical clocks. It is a fitting place for a debate about the heavens. In a large conference hall, thousands of astronomers from the International Astronomical Union gathered. These were the keepers of the celestial definitions, the men and women who dedicated their lives to mapping the dark. The atmosphere was tense, not with anger, but with the heavy weight of a decision that had been delayed for too long. For decades, a small, icy world at the edge of our solar system had held the title of planet. Pluto, discovered in 1930 by Clyde Tombaugh, a young farm boy turned astronomer, Pluto was the outlier. It was the odd one. While the other planets moved in neat, circular tracks on the same flat plane, Pluto's orbit was tilted. It was elongated, crossing inside the orbit of Neptune for 20 years at a time. It was tiny, smaller than our own moon, yet we loved it. We embraced it as the ninth sibling. It was the underdog of the solar system, the lonely sentinel guarding the frontier. But science is not sentimental. Science is a process of refinement, of looking closer. As telescopes improved, as we sent cameras into the dark, we began to see that Pluto was not alone. It was not a lonely sentinel. It was merely the first and brightest member of a vast, crowded population. In the 1990s, astronomers began finding other icy rocks out there in the dark beyond Neptune. They found one, then 10, then hundreds. They called this region the Kuiper Belt. It was a second asteroid belt, vast and cold, filled with debris left over from the formation of the solar system. Suddenly, Pluto didn't look like a planet anymore. It looked like a king of the Kuiper Belt. It was just the largest rock in a field of rocks. And then, the inevitable happened. Astronomers found something out there that rivaled Pluto in size. They named it Eris. Eris was icy, distant, and massive. If Pluto was a planet, surely Eris was too. And if Eris was a planet, what about Makemake? What about Haumea? What about Sedna? The list threatened to grow from 9 to 12 to 20 to hundreds. The word planet was about to lose its meaning. And so, in Prague, the vote was cast. Hands were raised. Yellow cards were held aloft. And in a moment that rippled through classrooms and textbooks around the world, Pluto was demoted. It was reclassified. It was no longer a planet. It was a dwarf planet. This decision was met with outcry from the public. People felt a genuine sense of loss, felt like a friend had been exiled. But for the astronomers, it was a moment of clarity. It was an admission that nature is more complex than our simple labels. It was an acknowledgement that we had been looking at the solar system with low-resolution glasses, and now, finally, the picture was sharpening. The universe is calm, even when it is strange. The Pluto controversy was our Einstein-like moment for planetary science. Just as Einstein showed us that time and space were not absolute, the Pluto decision showed us that planet is not a physical property inherent to the object itself. You cannot chip off a piece of rock and test it to see if it is planet rock. Being a planet is about context. It is about relationships. It is about where you are and who you are with. A rock in the asteroid belt is an asteroid. That same rock, if it were alone in deep space, might be something else entirely. Context matters. This realization was a crack in the foundation of our intuition. We tend to think of things as having fixed identities. A cup is a cup. A tree is a tree. But in astronomy, identity is fluid. Identity depends on gravity, on orbit, on the company you keep. This is a profound shift in perspective. It asks us to look at the relationships between things, not just the things themselves. Consider the scale of what we are talking about. Pluto is billions of miles away. It is so distant that the sun is just a bright star in its sky. It takes 248 Earth years to complete one orbit. Since its discovery in 1930, Pluto has not even completed half a lap around the sun. It moves in slow motion, indifferent to our debates. Whether we call it a planet, a dwarf planet, or an icy rock, it remains exactly what it is. A world of nitrogen ice mountains, frozen plains, and a thin, hazy atmosphere. It has a heart-shaped glacier on its surface, beating slowly with the rhythm of sublimation and freezing. It has moons that dance around it in a chaotic ballet. The label we give it changes nothing about the world itself. It only changes us. It changes how we organize our knowledge. It forces us to admit that the solar system is not a finished family of 9, but a dynamic, evolving environment with blurry edges. It forces us to be humble. Imagine standing on the surface of Pluto right now. The ground is hard as steel, made of water ice. The mountains rise up, jagged and sharp, because there is no rain to wear them down. The sky is black, even at noon. The sun is a piercing point of light, casting long, stark shadows that stretch for miles. It is quiet. There is no wind to speak of, only the thinnest whisper of nitrogen gas. It is a world of utter stillness, frozen in time. And yet, it is beautiful. It is complex. It has geology. It has history. Does this world care about the vote in Prague? Does the ice care if it is planetary ice or dwarf planetary ice? Of course not. The universe exists independently of our taxonomy. We build boxes to put things in, but the things often spill over the sides. The Pluto moment was simply the universe gently pushing back against our boxes. It was a reminder that we are the ones who need the labels, not the stars. What feels fixed is often only familiar. This disruption, this crack in our certainty, is where the real beauty of science lies. If we knew everything, if every category was perfect and eternal, science would be dead. It would be a museum of facts. But science is alive because we are constantly rewriting the dictionary. We are constantly finding exceptions to the rules. The demotion of Pluto was not a loss. It was a graduation. It was the moment we graduated from a simple, childlike view of the solar system to a mature, nuanced understanding. We realized that there is a continuum of objects. There are grains of dust. There are pebbles. There are boulders. There are asteroids. There are dwarf planets. There are rocky planets. There are gas giants. There are brown dwarfs. And there are stars. Where does one category end and the next begin? The lines are drawn in sand, and the tide of discovery is always coming in. As you listen to this, let the tension of the definition fade away. You don't need to decide if Pluto is a planet. You don't need to take a side. You can simply appreciate the variety. You can appreciate that our solar system produces such a range of worlds, from the massive, crushing gravity of Jupiter to the tiny, icy silence of Pluto. Each one is a unique expression of the same laws of physics. Each one tells a different story of formation and evolution. The crack that opened in 2006 let the light in. It allowed us to see the Kuiper Belt for what it is, a vast, unexplored frontier, teeming with worlds we have yet to name. It reminded us that we are still explorers. We are not just cataloging what we already know. We are hunting for what we don't. And that is a thrilling thought to hold in your mind as you drift toward sleep. The map is not finished. The inventory is not complete. There are still wonders waiting in the dark. We often think of planetary science as something that happens out there, in the cold void, disconnected from our daily lives. We imagine astronomers in high-altitude observatories, shivering in the cold, peering through brass eyepieces. Or we imagine robotic probes sailing silently through the vacuum, millions of miles from the nearest human hand. And while those images are true, the reality of the planets is much closer to you than that. In fact, you are likely holding proof of it in your hand right now, or it is resting on the nightstand beside you. Your smartphone is a marvel of engineering, but it is also a pocket-sized observatory. Consider the GPS, the global positioning system, that guides you to the grocery store or tracks your morning run. This system relies on a constellation of satellites orbiting Earth. But to work, these satellites must account for the curvature of spacetime caused by the mass of our planet. They must account for the fact that Earth is not a perfect sphere, but an oblate spheroid, bulging at the equator. They rely on a precise model of the planet you are standing on. Let's pause here for a moment and truly appreciate what this means. Right now, as you lie in bed, there are at least 4 satellites passing overhead, moving at about 8,500 miles per hour. Each one carries an atomic clock so precise that it loses only 1 second every 100,000 years. These clocks are ticking in orbit, broadcasting their timestamps to your phone. But here is the remarkable part. Those clocks in space are running faster than the clock on your nightstand. Time itself moves at different speeds depending on where you are in a gravitational field. Einstein predicted this. His theory of general relativity tells us that the stronger the gravity, the slower time moves. Down here on Earth's surface, deep in the planet's gravitational well, our clocks tick slightly slower than those flying high above us. The difference is tiny, only about 38 microseconds per day, but it adds up. If GPS satellites didn't correct for this relativistic effect, your location would drift by about 6 miles every single day. By the end of a week, your phone would think you were in a different city entirely. So when you tap that little blue dot on your screen, When you ask your phone, "Where am I?" you are asking a question that can only be answered by understanding the shape of the planet beneath you, the pull of its gravity, and the warping of spacetime itself. You are navigating not just through space, but through the fabric of reality. The planet is not just beneath you, it is part of the calculation that defines your position. Without the deep understanding of planetary physics, gravity, mass, rotation, the map on your phone would drift by miles every day. The little blue dot that represents you is held in place by equations derived from observing the heavens. When you look at that blue dot, you are looking at a direct application of planetary science. You are using the planet's geometry to find your way home. Think about the weather app you check before you get dressed in the morning. Those swirling radar maps, the predictions of rain or shine, they come from satellites looking down at Earth as a planet. They treat the atmosphere as a fluid dynamics problem on a rotating sphere. The science used to predict a thunderstorm in Chicago is the same science used to model the Great Red Spot on Jupiter or the dust storms on Mars. Meteorology is planetary science turned inward. Consider the satellites themselves for a moment. The GOES weather satellites, geostationary operational environmental satellites, hover 22,236 miles above the equator, matching Earth's rotation perfectly so they appear to stay in one place in the sky. From that vantage point, they watch an entire hemisphere at once. They see the planet as a sphere, clouds swirling in vast spirals driven by the Coriolis effect, the apparent deflection caused by Earth's rotation. Hurricanes spin counterclockwise in the northern hemisphere and clockwise in the southern, all because we live on a spinning ball. The algorithms that predict tomorrow's weather are planetary models in miniature. They divide the atmosphere into a three-dimensional grid, millions of tiny boxes stacked from the surface to the edge of space. They calculate the temperature, pressure, humidity, and wind in each box. Then they step forward in time, using the same physics that governs the atmospheres of Venus, Mars, and Titan. When your phone tells you to bring an umbrella, it is running a simulation of planetary fluid dynamics. It is treating Earth as what it truly is: a world with weather systems that span thousands of miles, driven by the uneven heating of a spherical surface tilted on its axis. Even the camera in your pocket owes a debt to the stars. The digital sensors that capture your family photos, charge-coupled devices, or CCDs were heavily developed and refined for astronomy. Astronomers needed a way to capture faint light from distant galaxies, far more sensitive than film. This technology trickled down, became cheaper, became smaller, and now sits on the back of your phone. When you take a picture of your cat sleeping in a sunbeam, you are using a tool sharpened by the need to see the edge of the universe. The journey from telescope to phone is a beautiful story of human ingenuity. In the 1960s and 70s, astronomers were frustrated. Photographic plates, glass sheets coated with light-sensitive chemicals, could capture images, but they were inefficient. They missed most of the light that hit them. A CCD, by contrast, converts nearly every photon into a signal. It is like the difference between trying to catch rain in a colander versus a bucket. For astronomers studying faint nebulae and distant quasars, this was transformative. NASA and observatories invested heavily in CCD technology. The Hubble Space Telescope, launched in 1990, carried sophisticated CCD cameras that allowed us to see deeper into space than ever before. The technology improved, the manufacturing processes were refined, and eventually CCDs became cheap enough to mass produce. By the early 2000s, they were in consumer cameras. Now they are in your phone, taking portraits with a clarity that would have stunned astronomers just a generation ago. You carry the legacy of planetary exploration in your pocket, using cosmic technology to capture birthday parties and sunsets. If you have an astronomy app, you can point your phone at the floor and see the stars that are currently shining on the other side of the world. You can point it at the wall and see where Mars is rising. This is not magic. It is data. It is centuries of observation codified into algorithms. Your phone knows exactly where Earth is in its rotation, exactly where it is in its orbit around the Sun, and exactly where the other planets are in relation to us. It is constantly calculating the dance of the solar system in the background, quietly, while you check your emails. These apps use something called ephemerides, tables of celestial positions calculated years in advance with stunning precision. They know that on this exact night, at this exact minute, Jupiter is precisely 31.7 degrees above the southwestern horizon from your location. They know this because we have watched the planets for thousands of years, measured their movements with ever-increasing accuracy, and boiled it all down to mathematical equations. The motion of the planets is so predictable that we can tell you where Mars will be on your birthday 50 years from now. We can calculate the positions of Venus, Saturn, and Neptune for any date in history or future, accurate to within a few arcseconds. Your phone's gyroscope and accelerometer tell it which way you are pointing. This GPS tells it where you are standing on the planet. The clock tells it what time it is. Combine those three pieces of information with the ephemerides, and suddenly your phone can overlay the night sky on your camera view in real time. You are seeing through the Earth, using the accumulated knowledge of civilizations who watched the wanderers cross the zodiac. What feels fixed is often only familiar. The sky appears fixed, but in truth everything is moving. Earth is spinning, the planets are orbiting, the stars are drifting through the galaxy. We have learned to track this cosmic choreography so well that we can put it in your hand. This connection goes deeper. The silicon in the chips of your device was forged in the hearts of dying stars billions of years ago. The gold in the connectors was created in the violent collision of neutron stars. The plastic case is made from oil, the ancient remains of life that flourished on this planet millions of years ago, powered by sunlight from the same star that warms us today. You are holding a piece of the cosmos. You are holding a geological and astronomical artifact. Let's trace this ancestry more carefully, because it is worth dwelling on. Every atom heavier than hydrogen in your phone, every carbon, nitrogen, oxygen, silicon, and iron atom was created inside a star. Not our sun, but previous generations of stars that lived and died long before our solar system even existed. Stars are fusion furnaces. In their cores, they squeeze hydrogen atoms together so tightly that they fuse into helium, releasing tremendous energy. This is the light that warms us. As a star ages, it fuses helium into carbon, carbon into oxygen, and so on, climbing up the periodic table. But fusion stops at iron. Iron is the end of the road. Fusing it costs energy instead of releasing it. So when a massive star has an iron core, it is doomed. The core collapses in a fraction of a second, then rebounds in a supernova explosion, one of the most violent events in the universe. In that explosion, in the unimaginable heat and pressure, the heaviest elements are forged. Gold, platinum, uranium, all the atoms too heavy for a star to make, are created in those final seconds. The silicon in your phone's processor was made in a supernova roughly 5 billion years ago, before the sun even existed. It was ejected into space as a glowing cloud of gas and dust. That cloud drifted for millions of years, mixed with other clouds, and eventually began to collapse under its own gravity. The center became the sun. The outer disk became the planets. Earth accreted from trillions of tiny collisions of dust, pebbles, and rocks. And buried in that dust was silicon, waiting patiently for 4.5 billion years until humans dug it up, purified it, and etched transistors onto its surface. The same is true for the gold contacts in your phone's circuitry. That gold was likely created in the collision of two neutron stars, dead stellar remnants so dense that a teaspoon would weigh as much as a mountain. When neutron stars collide, they don't just explode. They briefly create conditions so extreme that heavy elements rain out like cosmic confetti. This gold traveled across the galaxy, became part of a nebula, condensed into the early solar system, and sank into Earth's interior. Billions of years later, geological processes brought it near the surface, humans mined it, and now it sits in your hand, conducting electrons. You are holding stardust. Literally, the atoms in your phone are older than the Earth itself. They have been on a journey through space and time that staggers the imagination. And they end up here, in this quiet room, helping you navigate the streets of your city or check the time. The universe is calm, even when it is strange. In the United States, we are surrounded by monuments to this connection. The Jet Propulsion Laboratory in California, where rovers are built to drive on Mars. The Goddard Space Flight Center in Maryland, where satellites are managed. The giant radio dishes of the Deep Space Network, listening for whispers from the Voyager probes that have now left the solar system entirely. These are not just government buildings, they are bridges. They are the places where the human mind reaches out to touch the alien. And the data they gather flows back to us, eventually landing in the palm of your hand. Let's visit the Deep Space Network for a moment in our minds. There are 3 locations: Goldstone in California's Mojave Desert, Madrid in Spain, and Canberra in Australia. These 3 sites are spaced roughly 120 degrees apart around the planet so that as Earth rotates, at least one of them always has line of sight to deep space. They work in shifts like lighthouse keepers, maintaining contact with our distant robotic explorers. The radio dishes are enormous, some as large as 230 feet across, and they can detect signals so faint it is almost inconceivable. When Voyager 1, now over 15 billion miles away, transmits data back to Earth, its signal is received with a power of about 0.00000000000000000001 watts. To put that in perspective, the energy from all the photons collected from all the distant galaxies ever photographed by all the telescopes in history would not power a single light bulb for a single second. Yet we can hear Voyager 1's whisper across the solar system. The data, information about magnetic fields, solar wind, cosmic rays, travels from Voyager to the dish, from the dish to a control room, from the control room to NASA servers, and eventually to researchers' computers, and sometimes summarized to your phone as a news notification. Voyager 1 has entered interstellar space. You read it in bed, scroll past it, maybe think cool, and move on. But that single sentence represents a signal that traveled for 21 hours at the speed of light, was captured by a machine sensitive enough to hear a whisper from 1 trillion miles away, and was decoded by algorithms that understand the language of a spacecraft built in the 1970s. A planet is both a thing and a question, and the questions we ask echo across billions of miles. When you see a notification about a supermoon or a meteor shower, that is a reminder. It is a reminder that your schedule, your calendar, your days and nights are dictated by the motions of celestial bodies. Our week has 7 days because the ancients saw 7 moving objects in the sky: the Sun, the Moon, Mars, Mercury, Jupiter, Venus, Saturn. Sunday, Moon Day, Mars Day. The etymology is buried, but the connection remains. We live in a rhythm set by the planets. Let's dig into that calendar a bit more, because it is a beautiful fossil of ancient planetary observation. The 7-day week has no astronomical basis in the modern sense. Earth's rotation gives us the day, the moon's orbit gives us the month, Earth's orbit gives us the year, but 7 days? That comes purely from the 7 wandering lights our ancestors saw in the sky. Sunday is the sun's day. Monday is the moon's day. In Latin languages, the connection is even clearer: Martes, Mars; Mercredi, Mercury; Judy, Jupiter/Jove; Vendradi, Venus. In English, we have Tuesday, TIW, the Norse equivalent of Mars; Wednesday, Woden/Odin, equivalent to Mercury; Thursday, Thor, equivalent to Jupiter; and Friday, Freya, equivalent to Venus. Saturday remains Saturn's day in English. So every time you plan your week, you are invoking the planets. The names have been passed down through thousands of years, from Babylonian astrologers to Roman engineers to medieval monks to you, checking your phone in bed. The planets structured time for our ancestors, and they still do, hidden in plain sight. The cosmos organizes your life even when you are not paying attention. And the months themselves, those are lunar. The word month comes from moon. Most traditional calendars were lunar, tracking the 29.5-day cycle from new moon to new moon. We have since switched to a solar calendar for practical reasons, but the echo remains. The moon's gravitational pull creates the tides, which shaped the coastlines where civilizations grew, influenced fishing and farming, and gave us a reliable clock in the sky long before mechanical clocks existed. So, the planets are not just distant points of light. They are woven into the fabric of your Tuesday afternoon. They are in the technology that wakes you up. They are in the maps that guide you. They are in the calendar that organizes your life. A planet is both a thing and a question, and the answer to that question is relevant to every moment of your existence. Consider even the alarm clock that woke you this morning, or the clock on your nightstand that we imagined at the beginning. If it is a modern digital clock, it likely syncs with the internet via NTP, the Network Time Protocol. And where does internet time come from? Ultimately, from atomic clocks, many of which are maintained by GPS satellites orbiting overhead. Even your sense of what time it is depends on satellites that must account for planetary gravity and relativity. Time itself, as you experience it, is calibrated by planetary science. As you drift deeper into relaxation, let this thought ground you. You are not separate from the universe. You are a participant. Your daily life relies on the stability of Earth's orbit, the tilt of its axis, the protection of its magnetic field. You are a rider on a world that is functioning perfectly, sailing through the dark with reliable precision. The proof is in your pocket, but the reality is in your bones. That magnetic field, by the way, is another invisible gift of our planet. Earth's core is a churning mass of molten iron, spinning with the planet. This motion generates a magnetic field that extends tens of thousands of miles into space, creating an invisible shield called the magnetosphere. It deflects most of the charged particles streaming from the sun, the solar wind that would otherwise strip away our atmosphere and irradiate the surface. Mars lost its magnetic field billions of years ago, and its atmosphere thinned to almost nothing. Venus has no magnetic field, and its atmosphere is a toxic hellscape. But Earth's core keeps spinning, keeps protecting. A planetary heartbeat we never see but depend on every second. Compasses work because of this field. Migratory birds navigate by it. The auroras, the northern and southern lights, are the visible signature of it, glowing curtains of light that appear when solar wind particles slip through the magnetic poles and collide with our atmosphere. The planet is not just a lump of rock and water. It is a dynamic, protective system. It is alive in its own way, geologically and magnetically active, and we are nested safely within its influence. Let's take a moment to recap where we have been. We started with the simple intuition of the clock and the solid ground. We saw that intuition crack with the demotion of Pluto, realizing that our labels are fragile. And now, we have realized that the planets are not distant abstractions, but intimate parts of our technological and daily lives. We are building a ladder, rung by rung, from the familiar to the profound. Now we are ready to leave the Earth behind. We are ready to cast off the lines and sail into the deeper waters of definition and discovery. What lies ahead is a journey through the true nature of these worlds. The universe is calm, even when it is strange. Over the next hours, we will travel together through the quiet dark. We have plenty of time. There is no need to rush to the destination. The journey itself is the point. We will drift like a slow-moving probe, gathering data, observing wonders, and letting the vastness of the cosmos seep into our minds. Think of this as a gentle expedition, not a forced march. We are explorers of ideas, wanderers through concepts that have puzzled humanity for thousands of years. There is no test at the end. There is no prize for staying awake. The only goal is to let your mind expand outward, to feel the scale of what we are part of, and to find peace in that vastness. The universe is patient. It has been here for 13.8 billion years. Can wait while you breathe slowly and settle deeper into your pillow. Imagine we are boarding a ship together. Not a rocket with roaring engines and violent thrust, but something quieter. A vessel that moves through space without friction, without sound, propelled only by the gentle pull of gravity and the momentum of thought. The windows are wide, the cabin is warm, and outside the stars are waiting. This ship has no schedule. It moves at the pace of curiosity. If something catches your attention, we will linger there. If your mind drifts to sleep, the ship will continue on autopilot, carrying you safely through the dark. Our journey has waypoints, places we will visit, ideas we will touch. But these are not rigid stops. They are more like islands in a calm sea. We will approach each one slowly, circle it, observe it from different angles, and then drift onward. There is no rush. The cosmos is not going anywhere. It will be here tomorrow and the day after and a billion years from now. We are simply taking a moment to look at it closely, to appreciate its structure, and to understand our small but meaningful place within it. First, we will go back to the foundations. We will look at what it really is. We will strip away the poetry for a moment and look at the raw mechanics. What are the rules that make a planet? We will examine the 3 criteria set down by astronomers, the checklist that a world must pass to earn the title. We will visualize these rules with simple analogies, turning abstract physics into clear mental images. This is where we build our vocabulary. This is where we learn the language of planetary science, not in technical jargon, but in images you can hold in your mind. You will see how gravity shapes a world, how mass determines behavior, and how context defines identity. We will use the tools of thought experiments, mental sculptures that let you feel the physics without the equations. By the time we leave this waypoint, the 3 rules will feel intuitive, almost obvious. You will understand them in your bones, not just your brain. Then we will move to the experiments that changed our minds. We will visit the pivotal moments in history when our view of the universe shifted. We will stand next to Galileo in 1610 as he points his telescope at Jupiter and sees 4 tiny stars that refuse to stay put. We will watch the discovery of Ceres, the lost planet of the 19th century. We will witness the mathematical triumph of finding Neptune with a pen and paper before it was found with a lens. And we will jump to 1995, to the discovery that proved we are not alone in the universe, the first planet found orbiting another sun. These are not just historical footnotes. These are the moments when human perception cracked open and expanded. Each discovery was a tunhan to the system, a revelation that forced us to redraw the map of reality. Galileo saw moons orbiting another planet and realized Earth was not the center of all motion. The discovery of Ceres and its subsequent demotion taught us that nature creates more variety than our categories can hold. Neptune was found by trusting mathematics over eyesight, a profound act of faith in the invisible laws that govern motion. And 51 Pegasi B shattered our assumptions about what kinds of solar systems were even possible. As we visit these moments, you will feel the excitement and the vertigo. You will sense the courage it took to announce findings that contradicted common sense. You will appreciate the patience of astronomers who spent years, sometimes decades, staring at tiny points of light, waiting for them to reveal their secrets. These people were not superhuman. They were curious, stubborn, and willing to be wrong. They were willing to let the universe surprise them. From history, we will expand to the extremes. This is where the universe shows off. We will leave the comfort of our solar system and visit the freaks and the monsters of the galaxy. We will see hot Jupiters that orbit so close to their stars that their years last only days. We will see rogue planets drifting in eternal night. We will see worlds that blur the line between planet and star. This is the zoo of the cosmos, and it is far stranger than anything science fiction has dreamed up. Here, at the extremes, the rules we learned earlier will be tested to their breaking point. We will encounter planets made of materials that don't exist on Earth, worlds where the surface is an ocean of liquid diamond, or where the atmosphere is vaporized rock. We will visit tidally locked planets where one hemisphere is eternally day and the other eternally night, creating winds that scream across the Terminator at supersonic speeds. We will see super-Earths with crushing gravity, mini-Neptunes wrapped in thick hydrogen blankets, and brown dwarfs that are neither planet nor star but something in between. These extreme worlds remind us that Earth is not the template. It is one variation in an infinite theme. Our solar system, once thought to be the standard model, turns out to be somewhat unusual. We lack a super-Earth. We lack a hot Jupiter. Our planets are neatly spaced and move in orderly, circular orbits on the same plane. Out in the galaxy, chaos is more common. Planets migrate inward, crossing paths, ejecting siblings into the void. Some systems have planets that orbit backward. Some have planets around binary stars, figurating through complex gravitational fields. The universe is calm, even when it is strange, and the extremes show us just how strange it can be. Next, we will confront the paradoxes and the protections. We will look at the edge cases that still give astronomers headaches. We will look at moons that are bigger than planets. We will ask why a rock is a planet in one place but an asteroid in another. We will gently explore the hypotheses that try to resolve these contradictions, understanding that in science, A contradiction is just a door to a deeper truth. This is where we get philosophical. This is where we realize that the difficulty in defining planet is not a failure, it is a feature. It reflects the true complexity of nature. The universe does not come pre-labeled. It does not organize itself into neat categories for our convenience. It creates gradients, spectrums, and continua. We humans like boxes. We like to say this is A and that is B. But the universe prefers to create things that are 60% A and 40% B, or things that start as A and slowly become B over time. The paradoxes we will explore: Pluto's demotion, the moon-planet boundary, the exoplanet definition gap, are not problems to be solved so much as tensions to be appreciated. They teach us humility. They remind us that our models are maps, not the territory itself. A map is useful, but it is always incomplete. When we find something that doesn't fit the map, we have two choices: force it to fit or redraw the map. Science chooses the latter. We redraw the map. We update the definitions. We admit we were using a simplified picture and now we are ready for a more complex one. This section will also introduce the proposed solutions, the alternative definitions that different camps of astronomers are advocating for. The geophysical definition that says anything round is a planet. The dynamical definition that uses mathematical thresholds to determine dominance. The formation-based definition that asks, how was it born? None of these proposals has won yet. They all have strengths and weaknesses, and that is okay. Disagreement is not dysfunction. It is the engine of progress. What feels fixed is often only familiar, and right now the definition of planet is in flux. It is alive. It is evolving. And we are witnessing that evolution in real time. Finally, we will arrive at the frontier. We will stand at the very edge of human knowledge. We will look into the shadows for Planet 9, the hypothetical giant that might be lurking far beyond Pluto. We will ask how many Earth-like worlds are really out there. We will embrace the uncertainty, finding comfort in the fact that there are still mysteries left to solve. We don't know for certain, and that is a wonderful place to be. The frontier is where the excitement lives. It is where the map ends and the terra incognita begins. Here, we are not talking about settled science. We are talking about active investigations, about hypotheses that are being tested right now, about telescopes scanning the dark for signals that might arrive tomorrow or might never arrive at all. This is the bleeding edge. This is where the astronomers themselves are holding their breath, waiting to see what the universe will reveal next. We will talk about Planet 9, the ghost planet that might exist in the outer solar system, shepherding the orbits of distant icy bodies. The math suggests it is there. The observations suggest it is there. But no one has seen it yet. It is a puzzle written in gravity, and we are trying to solve it with patience and precision. If we find it, it will be a triumph of human ingenuity. If we don't, it will teach us something equally valuable: that the patterns we see can sometimes be mirages, and we must always be willing to question our assumptions. We will also gaze outward to the thousands of exoplanets now catalogued, and the millions more waiting to be discovered. We will ask the biggest question of all: are we alone? How common are planets like Earth? How many have water? How many have atmospheres that could support life? The James Webb Space Telescope and other next-generation instruments are beginning to answer these questions. They are sniffing the air of distant worlds, looking for the chemical signatures of biology. We are on the cusp of a discovery that could change everything. Or we might find that life is rare, precious, and fragile. Either answer will be profound, and we will consider the rogue planets, the wanderers that orbit no star, drifting through the interstellar void in darkness and silence. Recent studies suggest there may be billions of them, outnumbering the stars themselves. What are they like? Could they harbor life in subsurface oceans, warmed by internal heat? Could there be ecosystems that never see a sunrise, living in eternal night? These are questions we are only beginning to ask. A planet is both a thing and a question, and the frontier is full of unanswered questions. And when we are done, we will return to the clock. We will come back to the bedside table, to the rhythm of your breathing, and to the safety of sleep. We will close the loop, bringing the vastness of the universe back down to the scale of a single peaceful night. This return is important. We will have traveled billions of miles, both in space and in time. We will have visited worlds that rain rubies, stars that have died, and ideas that challenge civilizations. But in the end, we will always come home. We will return to the room, to the clock, to the quiet certainty that you are here, now, safe. The journey outward is exhilarating, but the journey inward, back to the breath, back to the body, back to the present moment, is where peace lives. The universe is vast, but you are here, and that is enough. This is our path. It is a gentle upward slope. We will climb it slowly, step by step. You don't need to memorize anything. You don't need to take notes. You just need to listen and let the images form in your mind. If you drift off at any point, that is perfectly fine. The planets will keep spinning whether you are watching them or not. Let the journey begin. There is no requirement to stay conscious for the entire voyage. In fact, drifting in and out is part of the experience. Think of it as sailing on a calm sea at dusk. Sometimes you watch the stars emerge. Sometimes you close your eyes and feel the gentle rocking of the waves. Both states are valuable. Both are restful. If you wake up later and find we are still talking about planets, you can rejoin us. If you sleep straight through to morning, you will wake up with the quiet sense that you traveled somewhere vast and returned safely. The journey will have happened in your subconscious, planting seeds of wonder that will bloom later, in unexpected moments. The clock continues its rhythm. Tick, tock, tick, tock. The room is warm. The darkness outside is soft. And the planets, those ancient wanderers, are moving in their orbits, indifferent to our attention, perfect in their mechanics. We are ready to begin. The universe is waiting, patient and calm. Let the journey unfold. So, what is a planet? If you stripped away the history, the culture, and the sentiment, what is the bare-bones definition? According to the International Astronomical Union, the governing body that made the decision in 2006, a planet must satisfy 3 specific conditions. Think of these as 3 gates that a celestial object must pass through to enter the club. Gate number 1. It must orbit the sun. This seems obvious, but it is the first filter. Our moon is large, round, and rocky. It looks like a planet. It has mountains and plains. But it orbits Earth, not the sun, so it is a moon. This rule establishes the hierarchy. The sun is the boss. The planets are the direct subordinates. Everything else is a subordinate of a subordinate. Gate number 2. It must be spherical. In technical terms, it must have sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a hydrostatic equilibrium shape. That is a mouthful. Let's simplify it. Imagine a small rock like an asteroid. It can be any shape, a potato, a dumbbell, a jagged shard. Gravity is too weak to crush it into a shape. But as an object gets bigger and heavier, its gravity gets stronger. Eventually, the gravity becomes so powerful that the rock itself begins to flow like a slow liquid. It pulls everything toward the center equally. The only shape where every point on the surface is equidistant from the center is a sphere. Think of a water balloon floating in a pool. The water pressure pushes out, the elastic skin pushes in, and it naturally settles into a round shape. A planet is like that, but the force pulling in is gravity. To be a planet, you must be big enough to have crushed yourself into a ball. You must have surrendered to your own weight. This is why planets are round. It is the shape of submission to gravity. Gate number 3. It must have cleared its neighborhood. This is the controversial one. This is the rule that killed Pluto. To be a true planet, you must be the gravitational bully of your orbit. You must be so massive that as you move around the sun, you either consume everything in your path or fling it away. You are the snowplow of the solar system. You keep your lane clean. Think of the early solar system as a dusty, crowded construction site. Rocks and gas were everywhere. As the planets formed, they grew bigger and bigger. Jupiter, being massive, cleared its lane completely. It ate the dust or kicked it out. Earth did the same. We move through a relatively empty highway. But Pluto lives in the Kuiper belt. Its lane is full of debris. It hasn't cleared anything. It is just one piece of rubble among millions. It is not the bully. It is just a member of the crowd. So, the definition of a planet is a celestial body that A, is in orbit around the Sun, B, has sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a hydrostatic equilibrium, nearly round shape, and C, has cleared the neighborhood around its orbit. Sounds dry, doesn't it? But there is a poetry in these rules. They tell the story of a world's life. Rule 1 is about belonging. Who do you dance with? Rule 2 is about maturity. Have you grown enough to find your shape? Rule 3 is about dominance. Have you carved out your own space in the chaos? A planet is a world that belongs to the Sun, has found its center, and walks a lonely path. Let's try a thought experiment. Imagine you could build a world. You start with a handful of dust. You add more and more. First, it's just a loose pile. Then, as it gets to the size of a house, gravity starts to hold it together loosely. It's still a lumpy mess. You keep adding. You make it the size of a city. Still lumpy. You make it the size of Texas. Now, things are getting interesting. The pressure in the center is building. But it's still not round. It looks like a giant potato. You keep going. You reach a critical threshold about 500 miles across. Suddenly, the rock in the center can't support the weight of the rock above it. Cracks, it shifts, it flows. The mountains slump. The valleys fill. The world sighs and settles into a sphere. Congratulations, you have passed gate 2. You are now a world. But are you a planet? Not yet. Now you have to look at your surroundings. If you are floating all alone in a clear patch of space, you might be a planet. But if you are surrounded by thousands of other rocks of similar size, you are just part of a belt. To be a planet, you need to keep growing. You need to become so heavy that your gravity acts like a vacuum cleaner, sucking up your neighbors, or a slingshot, throwing them into deep space. Only when you are truly alone in your orbit can you claim the title. This definition separates the major players from the minor ones. It distinguishes the architects of the solar system from the debris. It is not a perfect definition. As we will see later, nature loves to break rules, but it gives us a framework. It helps us understand the dynamics of the system we live in. A planet is both a thing and a question. The thing is the rock or gas ball. The question is, does it dominate its environment? Does it have the gravitational authority to rule its domain? Earth does. Jupiter definitely does. Pluto, lovely as it is, does not. As you process this, imagine the sheer scale of forces required to make a rock flow like water. Imagine the silence of space as a planet sweeps its orbit clean over billions of years. It is a slow, relentless process of tidying up the universe. Gravity is the great organizer, pulls dust into rocks, rocks into worlds, and worlds into orderly paths, creates calm out of chaos. What feels fixed is often only familiar. We thought planet was just a label for big thing, but now we see it is a label for a specific kind of gravitational dominance. It is a title that must be earned through billions of years of orbital mechanics. Our understanding of planets didn't appear overnight. It was built, brick, by people who looked at the sky and noticed something didn't fit. Let's travel back to 4 specific moments when the universe whispered a secret to us, and we were smart enough to listen. The first moment, January 1610, Padua, Italy. Galileo Galilei points his homemade telescope, a simple tube with lenses that magnified only 20 times, at the bright wandering star we call Jupiter. He expects to see a magnified point of light. Instead, he sees a disk, a world, and strung out in a line next to it, he sees 3 tiny stars. The next night, he looks again. The stars have moved. One has disappeared behind the planet. A 4th one has appeared. Over the next few weeks, Galileo realizes something that shatters the medieval worldview. These stars are not stars. They are moons. They are orbiting Jupiter. This was the first time we realized that Earth was not the only center of motion. It was the first proof that other worlds could have their own systems. Jupiter was like a mini solar system. If Jupiter had moons, maybe it was a world like Earth. The definition of planet expanded from wandering light to place. A a place with gravity, with companions, with complexity. The second moment, January 1st, 1801, Sicily. Giuseppe Piazzi discovers a moving object between Mars and Jupiter. He names it Ceres. It is faint, but it moves like a planet. Astronomers rejoice. They have found the missing planet between Mars and Jupiter. For 50 years, Ceres is listed in textbooks as a planet. It has a symbol. It has a place in the family. But then, they start finding other things in the same region. Pallas, Juno, Vesta. They are smaller than Ceres, but they are in the same orbit. Suddenly, Ceres doesn't look like a planet anymore. It looks like the biggest member of a crowd. It looks like debris. In the 1850s, the astronomical community made a tough call. They stripped Ceres of its planetary status and coined a new term, asteroid. Sound familiar? It is exactly what happened to Pluto 150 years later. History rhymes. We learned that sometimes a planet is just a big rock in a busy street. The third moment, 1846. Paris and Berlin. Astronomers had been tracking Uranus, the seventh planet, and noticed it was misbehaving. It wasn't moving exactly where Newton's laws of gravity said it should. It was speeding up and slowing down as if something invisible was tugging on it. A French mathematician, Urbain Le Verrier, sat down with a pen and paper. He calculated where a hypothetical eighth planet would have to be to cause these perturbations. He sent his calculations to an observatory in Berlin. "Look here," he said. That very night, the German astronomer Johann Galle pointed his telescope at the exact patch of sky Le Verrier indicated. And there it was, Neptune, a giant, blue, icy world, found not by scanning the sky, but by trusting the math. This changed everything. Proved that gravity is universal. It proved that we could see the invisible using only our minds. It cemented the idea that planets are massive, gravitational heavyweights that dictate the motion of their neighbors. The fourth moment, 1995.
Haute-Provence Observatory, France.
Michel Mayor and Didier Queloz are looking at a star called 51 Pegasi, about 50 light-years away. They are not looking for a planet. They are looking for a wobble. If a star has a planet, the planet's gravity should tug on the star, making it wobble back and forth. They find it, a wobble. But the data makes no sense. The wobble is fast, furious. It suggests a planet as big as Jupiter, but orbiting its star every 4 days. For days, Mercury takes 88 days. This planet is practically touching its star. It is being roasted. It defied every theory of planetary formation we had. We thought giant planets had to form far out in the cold. This hot Jupiter, named 51 Pegasi b, broke all the rules. This discovery opened the floodgates. It told us that our solar system is not the template for the universe. It is just one variety. There are systems with planets that orbit backward, systems with 2 suns, systems with planets made of lava. 51 Pegasi b taught us humility. It taught us that our imagination is far more limited than nature's creativity. These 4 moments, Galileo's moons, the demotion of Ceres, the math of Neptune, and the shock of 51 Pegasi b, are the pillars of our modern understanding. They show us that science is a living thing. It grows. It sheds old skins. Corrects itself. A planet is both a thing and a question, and the question keeps getting more interesting. As you rest, think of the patience of these astronomers. Galileo sketching by candlelight. Le Verrier covering pages with calculus. Mayor and Queloz checking their data again and again, terrified they were wrong. They were listening to the whispers of gravity. They were decoding the faint signals of the cosmos. And because of them, we know where we are. Now that we understand the rules, let's look at the rule breakers. Let's travel to the edges of what is possible. The universe is a vast laboratory, and it runs experiments at pressures and temperatures we can barely comprehend. The planets in our own solar system are diverse, but they are gentle compared to what lies beyond. Imagine a world called a hot Jupiter. We touched on this with 51 Pegasi b. These are gas giants, massive balls of hydrogen and helium that have migrated inward. They orbit so close to their stars that they are tidally locked. One side always faces the star, roasting in eternal day, while the other faces the cold of space. The winds on these worlds scream at thousands of miles per hour, carrying heat from the day side to the night side. On some of them, the clouds are made of vaporized rock. On the night side, it might rain liquid rubies and sapphires. It is a jewel box Hell's Cape, beautiful and terrifying. Then there are the super-Earths. These are rocky worlds like ours but scaled up. Imagine a planet twice the size of Earth with gravity twice as strong. If you stood on the surface, you would feel incredibly heavy. Mountains on these worlds would be lower, crushed by the intense gravity. The atmosphere might be thick and crushing. But these worlds might also be incredibly geologically active, with volcanoes erupting constantly, resurfacing the planet over and over. Are they habitable? We don't know. They are the most common type of planet in the galaxy, yet we don't have a single one in our own solar system. We are the odd ones for lacking a super-Earth. Consider the mini-Neptunes. These are worlds wrapped in thick blankets of gas, but smaller than Neptune. They might be ocean worlds, covered entirely in a deep, global sea hundreds of miles deep. Under that pressure, water behaves in strange ways. It might form exotic ices, Ice 7, Ice X, that are hot and solid at the same time. These are water worlds, but not like the oceans of Earth. They are high-pressure steam baths, shrouded in mystery. And then, the most lonely of all, the rogue planets. These are worlds that have been kicked out of their homes. Perhaps they formed in a chaotic young solar system and were flung out by a passing giant. Now they drift through the interstellar void, tethered to no star. They float in eternal darkness. Without a sun, their surfaces are frozen solid, near absolute zero. But deep inside, they might still be warm from the heat of their formation or from radioactive decay. Could there be life huddled deep underground on a rogue planet, unaware that the universe has stars? It is a haunting thought, a world without a sunrise, a world where night is the only state of being. There are even planets that orbit the corpses of stars. In 1992, before 51 Pegasi b, astronomers found planets orbiting a pulsar. A pulsar is a neutron star, the ultradense core of a star that exploded. It spins hundreds of times a second, blasting out beams of radiation. It is a cosmic lighthouse of death. Yet, incredibly, there are planets there. Poltergeist and Phobter are their names. They are bathed in lethal X-rays. They are dead worlds in a graveyard system. Yet they exist. Gravity holds them there, even after the death of their sun. And at the other end of the scale, we have the boundary between planet and star, the brown dwarfs. These are objects too big to be planets but too small to be stars. They are failed stars. They have some heat, they glow dimly in the infrared, but they never ignited nuclear fusion. They sit in the uncanny valley of astronomy. Are they superplanets? Are they mini-stars? Nature doesn't care about our labels. It just makes a continuum of mass. A brown dwarf is a bridge between the cold rock and the burning plasma. The universe is calm, even when it is strange. These extreme worlds remind us that our Earth is a rare and precious garden. We live in the Goldilocks zone. Not too hot, not too cold, not too big, not too small. We are balanced on a knife edge of probability. Seeing the extremes makes us appreciate the center. It makes the quiet ticking of the clock feel like a miracle of stability.
Let us do a micro recap.
We have defined a planet by the IAU rules: orbit, round, cleared neighborhood. We have seen how history changed our minds. Galileo, Ceres, Neptune, exoplanets. And now we have toured the zoo of extreme worlds: hot Jupiters, rogue planets, pulsar planets. We are seeing the full spectrum. These worlds are far away. You will never walk on them, but knowing they exist expands your inner map, creates space in your mind for wonder. It reminds you that the possibilities are infinite. A planet is both a thing and a question, and sometimes the answer is liquid ruby rain. With all this variety, you can see why the definition is struggling to keep up. The simple 3 rules we discussed earlier, orbit the sun, be round, clear the neighborhood, start to fray at the edges when we look closely. we enter the realm of paradoxes. A paradox, in its gentlest form, is not a failure of logic. It is a signpost. It points to the places where our categories are too simple for the complexity of reality. When we encounter a paradox in planetary science, we are not discovering that we were wrong. We are discovering that we were incomplete. We were looking at a corner of the picture and calling it the whole frame. The paradoxes invite us to step back, to widen our view, and to appreciate the full, messy, beautiful spectrum that nature has created. Let's walk through these paradoxes slowly, one at a time, like exhibits in a quiet museum. There is no need to solve them tonight. We are simply here to witness them, to understand why they matter, and to feel the gentle tension they create in our understanding. The Pluto paradox is the most famous. We've discussed it, but let's look deeper. If Earth were in Pluto's orbit, would it be a planet? The Kuiper belt is vast. To clear that neighborhood requires immense gravity. Earth might not be big enough to clear it. So, is planethood about the object or the location? If you are a planet here but a dwarf planet there, is the label meaningful? This bothers some people. It feels like calling a tiger a house cat, just because it lives in the jungle instead of a zoo. Let's do a thought experiment. Imagine we could pick up Earth, gently, carefully, and move it out to where Pluto orbits, about 40 times farther from the Sun than we are now. Would Earth still be a planet? According to the third rule, clear the neighborhood, it might not qualify. The Kuiper belt is densely populated with icy bodies. Earth's gravity, formidable as it is in our current location, might not be strong enough to dominate that distant, crowded region. We would become a dwarf planet overnight, simply by changing our address. Conversely, imagine we could move Jupiter to where Earth is. Jupiter is so massive that it would clear the Kuiper belt from here. Its gravity would reach across billions of miles and eject or capture every rock out there. So Jupiter would be a planet no matter where you put it, but Earth's status is conditional. This feels unfair, doesn't it? It suggests that being a planet is not an intrinsic property. It is relational. It depends on where you are and what surrounds you. A planet is both a thing and a question, and part of the question is, where do you live? Some planetary scientists argue that this makes the definition flawed. They say a world should be defined by what it is, not where it is. If Pluto has mountains, plains, an atmosphere, and complex geology, does it matter that it shares its neighborhood with other rocks? Does the existence of siblings diminish your identity? This is the emotional core of the Pluto debate. It is not just about taxonomy. It is about whether we define things by their essence or their context. Then there is the moon paradox. Our moon is huge. It is bigger than Pluto. It is bigger than Eris. It is round. It has geology. If you plucked it out of Earth's orbit and set it around the Sun, it would instantly be called a planet. But because it orbits us, it is a moon. Titan, the moon of Saturn, has an atmosphere thicker than Earth's. It has lakes of liquid methane. It is a complex, active world. Ganymede, the moon of Jupiter, is bigger than the planet Mercury. Yet Mercury is a planet, and Ganymede is a moon. Is this fair? Is it useful? Or is it just a quirk of history? This paradox reveals the hierarchical nature of our solar system. We have decided that the primary relationship is with the Sun. If you orbit the Sun directly, you are a planet or dwarf planet. If you orbit something that orbits the Sun, you are a moon, regardless of your size or complexity. But this hierarchy is arbitrary. It is a human construct designed to keep the categories manageable. Nature does not care about hierarchy. Nature creates bodies of all sizes, orbiting in all configurations, and each one is simply doing what gravity tells it to do. Consider Titan for a moment. It has weather. It has seasons. It has rain, rivers, lakes, and seas, not of water, but of liquid methane and ethane. It has a nitrogen atmosphere, the only moon in the solar system with a thick atmosphere. It has organic chemistry happening on its surface, building complex molecules that might be precursors to life. It is, in every practical sense, a world. Yet we call it a moon because it orbits Saturn. Does the label moon capture the majesty and complexity of Titan? Does it do it justice? And then there is the strange case of Ganymede and Mercury. Ganymede, Jupiter's largest moon, has a diameter of 3,273 miles. Mercury, the smallest planet, has a diameter of 3,032 miles. Ganymede is bigger. Ganymede even has its own magnetic field, something Mars lacks. If size were the criterion, Ganymede would be promoted and Mercury might be questioned. But Mercury orbits the Sun, and Ganymede orbits Jupiter, so the roles are set. The universe is calm, even when it is strange, and this strangeness forces us to ask, what are we really measuring when we define a planet? And what about the exoplanet definition challenge? The IAU definition specifically says, orbits the Sun. It doesn't say orbits a star. So technically, officially, 51 Pegasi b is not a planet. It is an exoplanet. This is a linguistic trap. We all know they are planets, but the legal text hasn't caught up to the discovery. We are using a dictionary written for one solar system to describe a galaxy of billions. This is more than a technicality. It reveals a deep truth about how science evolves. The 2006 definition was written in the context of our own solar system. The committee in Prague was focused on Pluto, Eris, and the Kuiper belt. They were not thinking about the thousands of exoplanets that were already known by then. They were solving a local problem, and they wrote a local solution. But the universe is not local. The rules we write for our backyard do not necessarily apply to the neighbor's yard, let alone the next city, the next country, or the next galaxy. So now we have an awkward split. Planets in our solar system are defined by one set of rules. Planets around other stars are called exoplanets, but have no formal IAU definition. They are defined loosely by mass. If an object is less than 13 times the mass of Jupiter, and it orbits a star, we call it a planet. If it is heavier than that, it might be a brown dwarf, a failed star. But this mass boundary is fuzzy and based on theory, not observation. What feels fixed is often only familiar. There is also the binary planet problem. Pluto and its largest moon, Charon, are almost the same size. Charon is about half the diameter of Pluto. They do not orbit around each other in the traditional sense. Instead, they orbit a point in space between them, a barycenter that lies outside of Pluto itself. This makes them a binary system. Some scientists argue that Pluto and Charon should be considered a double dwarf planet. But the IAU rules do not account for this. The definition assumes a clear hierarchy: planet and moon. It does not contemplate equals dancing together. And what about worlds that do not orbit anything? The rogue planets we discussed earlier, those lonely wanderers drifting through interstellar space. Are they planets? They do not orbit a star. They do not orbit the Sun. According to the strict definition, they fail the first criterion. Yet they are round, they have mass, they have geology. They are worlds in every sense except gravitational allegiance. If a planet loses its star, does it lose its identity? Is it demoted to former planet? Or is it simply a planet in exile? How do we resolve this? Scientists have hypotheses. They have proposals. Proposal 1, the geophysical definition. This camp says, forget the orbit. Look at the body. If it is big enough to be round and not big enough to be a star, it is a planet. Period. Under this definition, Pluto is a planet. Ceres is a planet. The Moon is a planet. Titan is a planet. Our solar system would have over 100 planets. It would be a crowded map, but it would be consistent. A potato is a potato whether it is in a field or a sack. A world is a world. This definition is championed by planetary geologists, the scientists who study the surfaces, interiors, and processes of worlds. They argue that what matters is the physics of the body itself. A round object is round because its internal structure is dominated by gravity. It has differentiated into layers: a core, a mantle, and a crust. It has geological processes: volcanism, tectonics, erosion. It is, in their view, a world. And worlds deserve to be called planets, regardless of their postal code in the solar system. The advantage of this definition is clarity and inclusivity. It is easy to apply. You measure the diameter and the shape, and you know the answer. treats all bodies equally. The disadvantage is that it creates a very long list. Our solar system would have well over 100 planets, and the number would keep growing as we discover more objects. Textbooks would struggle. Teachers would struggle. But the geophysicists argue that complexity is not a reason to avoid truth. If nature made 100 worlds, we should acknowledge 100 worlds. Proposal 2. The dynamical definition. This camp sticks to the current rules but refines them mathematically. They calculate a discriminate value, a number based on mass and orbit that tells you if a body dominates its zone. It draws a sharp mathematical line. Earth is clearly above the line. Pluto is clearly below. Keeps the club exclusive. It focuses on the architecture of the system, not the individual members. This definition is favored by dynamicists, the scientists who study orbits, gravitational interactions, and the long-term evolution of planetary systems. They argue that what matters is how a body shapes its environment. A true planet is a gravitational architect, carves out a zone of influence. It bends the orbits of everything nearby. It is, in their view, a force of order in the chaos of the early solar system. The advantage of this definition is that it preserves the current structure and adds mathematical rigor. The discriminate value, often called the Stern-Levison parameter or the marginal parameter, can be calculated for any object. Earth's value is about 1.5 million. Pluto's value is about 0.003. The gap is enormous, and there is no ambiguity. The disadvantage is that it is location dependent. A body's planetary status changes if you move it, which feels philosophically uncomfortable to some. But the dynamicists argue that context is everything. A lion in a zoo is not the same as a lion on the savannah, even if it is the same animal. The role defines the identity. Proposal 3. The formation definition. This camp asks, how was it born? Did it form like a star, collapsing from a gas cloud? Or did it form like a planet accreting from dust in a disk? If we could determine the birth story of an object, maybe that defines what it is. But birth stories are hard to read billions of years later. The evidence is erased by time. This definition is favored by theorists, the scientists who model the formation of solar systems. They argue that the process of birth determines the nature of the object. Stars and brown dwarfs form from the direct collapse of gas clouds. Planets form from the slow accumulation of solid material in a protoplanetary disk. These are two fundamentally different processes, and they should result in two different categories. The advantage of this definition is that it is based on physical processes, not arbitrary cutoffs. The disadvantage is that it is nearly impossible to observe. Once a world is 4 billion years old, its birth certificate is long gone. We have to infer formation history from indirect clues, and those clues are often ambiguous. There is even a proposal for, less discussed but intriguing, the cultural definition. This camp argues that planet is not a scientific term at all. It is a cultural one. It is a word we use to organize our understanding, like continent or ocean. The boundaries of continents are debated. Is Europe really separate from Asia? The answer depends on culture, history, and convention, not geology. Similarly, the boundaries of planet might be best decided by consensus and tradition, not by rigid rules. Under this view, Pluto is a planet because we have called it one for 76 years, and that cultural inertia is valid and meaningful. There is no consensus yet, and that is okay. In fact, it is healthy. It means we are thinking. The paradoxes protect us from arrogance. They remind us that nature is subtle. The universe creates spectrums, humans create bins. The friction comes when we try to force the spectrum into the bin. What feels fixed is often only familiar. Science is not a finished cathedral. It is a construction site. We are constantly building, tearing down, and rebuilding our understanding. The paradoxes are not cracks in the foundation. They are expansion joints. They allow the structure to flex and grow without breaking. The fact that we are still arguing about the definition of planet in the 21st century is not a sign of failure. It is a sign of vitality. It means we are still discovering. It means the universe still has the power to surprise us. As you listen, imagine the solar system not as a list of names, but as a dance. The big dancers swing wide and clear the floor. The little dancers weave in and out, finding their own paths. The moons spin around the planets like partners in a waltz. It is a dynamic, moving system. The labels are just name tags we stick on the dancers. The dance goes on regardless. Let's take a moment to recap. We have seen that the definition of planet creates paradoxes when applied to edge cases. We have seen that Pluto's status depends on location, that moons can be larger than planets, that the definition does not cover exoplanets or rogue planets, and that binary systems defy the hierarchy. We have explored 4 different proposals for resolving these paradoxes, each with its own logic and limitations. And we have realized that the lack of consensus is not a problem. It is a reflection of the true complexity of nature. The universe is calm, even when it is strange, and the paradoxes are part of the calm. We have reached the edge of the map. We are now standing at the frontier, peering into the fog of the unknown. This is where the next big discoveries will be made. This is where the planet question is most alive. The frontier is not a place. It is a state of mind. It is the boundary between what we know and what we suspect. It is the realm of hypotheses, of telescope time requests, of late nights in observatory control rooms, of algorithms combing through data for patterns. It is where the astronomers are holding their breath. It is where the next textbook chapter is being written, line by line, observation by observation. There is a special kind of peace in standing at a frontier. Behind you is the solid ground of knowledge, the confirmed planets, the mapped orbits, the tested theories. Ahead of you is the mist of possibility. You cannot see what is out there, but you can see the clues. You can see the footprints in the snow. You can hear the faint whispers carried on the wind. And you can choose to step forward into the unknown, or you can rest here, on the threshold, and simply appreciate the vastness of what remains to be discovered. Tonight, we will do both. We will explore the leading edges of planetary science, the questions that are actively being researched right now in observatories and universities around the world. But we will do it gently, without urgency, savoring the uncertainty the way you might savor the moment before opening a gift. The universe is patient. The answers will come when they come. For now, we can simply admire the questions. Somewhere out there, far beyond Pluto, deep in the dark, there might be a ghost. Astronomers have noticed strange alignments in the orbits of distant Kuiper belt objects. Sedna and a handful of other rocks seem to be clustered together, their orbits tilted in the same way. It is unlikely to be a coincidence. It looks like they are being shepherded by something massive, something invisible. This is the Planet 9 hypothesis. The math suggests there could be a planet about 5 to 10 times the mass of Earth, a super-Earth or mini-Neptune, orbiting hundreds of times further out than Earth. It would take 10,000 years to complete one orbit. It would be frozen, dark, and silent. We haven't seen it yet. It is too faint, too slow. But the gravity ghost is there. Telescopes are hunting for it right now. If we find it, it will be the 3rd time in history we found a planet by math after Neptune. It would rewrite the solar system again. It would be the true 9th planet, restoring the number we lost. Let's sit with this idea for a moment. Imagine a world 5 times more massive than Earth, orbiting so far from the sun that the sun itself appears as just a bright star. No disk, no warmth, just a point of light in an otherwise black sky. At that distance, sunlight is 10,000 times dimmer than what we experience here. It is perpetual twilight, but a twilight that would seem like full night to our eyes. The temperature on this world would be only a few dozen degrees above absolute zero, the coldest possible temperature in the universe. If Planet 9 exists, it is probably an ice giant similar to Uranus or Neptune, but even colder. It might have been formed closer to the sun, in the same region where the other giant planets formed, and then been ejected outward by a gravitational encounter. A cosmic billiard shot that sent it careening into the outer dark. Or it might have formed out there, from the slow accumulation of icy material in the distant reaches of the protoplanetary disk. Either way, it is alone now, tracing a vast ellipse that takes millennia to complete. The evidence for Planet 9 is indirect but compelling. Astronomers have catalogued several trans-Neptunian objects, rocks beyond Neptune, whose orbits are strangely aligned. Their perihelia, the closest points to the Sun, all point in roughly the same direction. Their orbital planes are tilted in similar ways. If these objects were distributed randomly, the odds of this clustering would be less than 1 in 1,000. Something is organizing them. Something with gravity. Konstantin Batygin and Mike Brown, the astronomers who proposed the Planet 9 hypothesis in 2016, ran computer simulations. They found that a planet of 5 to 10 Earth masses on a highly elongated orbit could create exactly the pattern we observe. It would act like a shepherd, nudging the smaller objects into alignment over millions of years. The math is elegant, the physics is sound, but the planet itself remains hidden. Why haven't we found it yet? Because the search space is enormous. Planet 9 could be anywhere in a huge swath of sky, and it moves so slowly that it is difficult to distinguish from background stars. Telescopes have to take images of the same patch of sky weeks or months apart, then compare them to see if anything has moved. It is like searching for a single black cat in a dark warehouse the size of a city. But the search continues. Observatories around the world are dedicating time to this hunt. The Vera C. Rubin Observatory, when it comes online, will survey the entire sky repeatedly, and it might finally catch the ghost. But we don't know for certain. Could be a planet. It could be a primordial black hole the size of a grapefruit, a wilder hypothesis. Could be a statistical illusion. We are waiting in the dark, listening for a whisper. The primordial black hole hypothesis is fascinating in its strangeness. Some physicists have suggested that if Planet 9 is not a planet, it could be a tiny black hole, one that formed in the first moments after the Big Bang, not from the collapse of a star. These primordial black holes, if they exist, could be scattered throughout the galaxy, invisible and undetectable except by their gravitational influence. One might have been captured by our solar system billions of years ago and now orbits quietly in the outer dark. It would have the same gravitational effect as a planet, but it would be only a few inches across. A dense knot of warped spacetime with no light, no heat, no surface. Just gravity. This hypothesis is speculative even by astronomical standards, but it is a reminder that the universe has more tricks up its sleeve than we can imagine. A planet is both a thing and a question, and sometimes the answer is maybe not a planet at all. Beyond our system, the frontier is about life. How common are Earth-like worlds? We know there are billions of planets in the galaxy, but how many are rocky? How many are in the habitable zone? How many have water? How many have atmospheres? The James Webb Space Telescope is starting to sniff the air of these distant worlds. We are looking for biosignatures, oxygen, methane, ozone. We are looking for the chemical fingerprint of breathing. Let's think about what this means. For all of human history until 1995, we did not know if planets were common or rare. We had one example, our own solar system. We could speculate, dream, and write science fiction, but we had no data. Then came the exoplanet discoveries, and suddenly we knew planets are everywhere. Nearly every star has at least one. The galaxy is full of worlds. But knowing that planets exist is only the first step. The next step is to characterize them, to understand what they are like. This is where the James Webb Space Telescope, JWST, comes in. Launched in December 2021, JWST orbits a point in space called L2, about 1 million miles from Earth. It is the most powerful telescope ever built, designed specifically to study the atmospheres of exoplanets. When a planet passes in front of its star, a transit, some of the starlight filters through the planet's atmosphere before reaching us. That light carries information. Different molecules absorb different wavelengths of light, leaving dark lines in the spectrum, like fingerprints. JWST can read those fingerprints. Water vapor leaves a fingerprint. Methane leaves a fingerprint. Carbon dioxide, ammonia, oxygen. All of them leave unique signatures. By reading these, we can build a chemical profile of a distant world without ever going there. We can ask, does it have an atmosphere? What is that atmosphere made of? Is it thick like Venus, or thin like Mars, or just right like Earth? And most tantalizing of all, Are there chemicals present that should not be there? Chemicals that can only be produced by living organisms? Oxygen is a biosignature. On Earth, nearly all the oxygen in our atmosphere is produced by photosynthesis, by plants, algae, and cyanobacteria converting sunlight, water, and carbon dioxide into sugars and oxygen. Without life constantly replenishing it, Earth's oxygen would react with rocks and disappear within a few million years. So if we find an exoplanet with significant amounts of oxygen in its atmosphere, it suggests that something is producing it. It suggests life, but we have to be careful. There are non-biological ways to produce oxygen. Intense ultraviolet radiation from a star can split water molecules, releasing oxygen. So we look for combinations of gases. Oxygen and methane together is a stronger signal, because these two gases react with each other and would not coexist for long unless something is replenishing them. On Earth, that something is life, methane from bacteria and oxygen from plants. If we find both on another world in significant quantities, it would be a very strong hint. JWST has already begun this work. It has studied the atmospheres of several exoplanets, including WASP-96b, a hot Jupiter with water vapor, and K2-18b, a mini-Neptune that might have a water ocean beneath a hydrogen atmosphere. The data is preliminary, the interpretations are cautious, but the process has begun. We are moving from the era of discovery to the era of understanding. We are learning to read the language of distant worlds. We are also realizing that the galaxy is full of rogue planets. Recent studies suggest there might be more rogue planets than stars. The Milky Way might be teeming with billions of lonely worlds, drifting in the dark. What are they like? Could they harbor life powered by internal heat? We are just beginning to detect them using microlensing, watching for the brief blip of gravity as they pass in front of a distant star. Rogue planets are difficult to study because they emit almost no light. They do not have a star to illuminate them, and they are too cold to glow in the infrared. So we detect them indirectly using a phenomenon called gravitational microlensing. When a massive object passes in front of a distant star, its gravity bends the light from that star, acting like a lens. For a few hours or days, the star brightens, then fades back to normal. By studying the exact pattern of this brightening, astronomers can infer the mass and distance of the object that caused it. In the past 2 decades, microlensing surveys have detected dozens of candidate rogue planets. They range in size from Earth-like to Jupiter-like. They drift through the galaxy, unbound to any star, tracing lonely orbits around the galactic center. Some of them might have been ejected from their birth systems, flung out by gravitational chaos. Others might have formed independently, collapsing from small pockets of gas that never grew large enough to become stars. Could life exist on a rogue planet? It sounds impossible. Without a sun, there is no photosynthesis, no warmth, no light. The surface would be frozen solid, colder than anywhere on Earth. But deep underground, it is a different story. A large planet retains heat from its formation for billions of years. Radioactive decay in its core generates additional heat. If the planet has a thick ice shell, that heat could melt the ice at depth, creating a subsurface ocean warmed not by a star, but by the planet itself. We have an example of this in our own solar system, Europa, the moon of Jupiter. Europa is covered in ice, but beneath that ice is a global ocean, kept liquid by tidal heating from Jupiter's gravity. Life in Europa's ocean, if it exists, would live in eternal darkness, feeding on chemical energy from hydrothermal vents on the ocean floor. A rogue planet could support a similar environment. Life there would never see a star. It would never know that the universe has light. It would live in an entirely self-contained world, powered by geology alone. The universe is calm, even when it is strange, and life, if it is out there, might be stranger than we imagine. We stand at a moment of transition. We are moving from the era of discovery, finding points of light, to the era of characterization, understanding them as worlds. We are moving from counting planets to knowing them. A planet is both a thing and a question, and the question is becoming, are we alone? This question, are we alone, is one of the oldest and most profound questions humanity has ever asked. For most of history, it was a philosophical question, debated by poets and priests. Now, for the first time, it is a scientific question. We have the tools to answer it. We have the telescopes to search for biosignatures. We have the probes to explore the moons of Jupiter and Saturn, where subsurface oceans might harbor microbial life. We have the mathematical models to estimate the number of habitable worlds in the galaxy. The answer might come tomorrow, or it might take another century. But the search is underway, and that alone is a miracle. The Drake equation, formulated in 1961 by astronomer Frank Drake, is an attempt to estimate the number of active, communicative civilizations in the Milky Way. It multiplies together several factors: the rate of star formation, the fraction of stars with planets, the number of planets per star that could support life, the fraction that actually develop life, the fraction that develop intelligent life, the fraction that develop technology, and the length of time such civilizations remain detectable. Most of these factors are still uncertain. But with every exoplanet discovery, with every atmospheric analysis, we refine the numbers. We move closer to an answer. It is a profound place to be. We are the generation that knows exoplanets exist. We are the generation that might find Planet 9. We are the generation that might detect the first breath of alien life. The universe is opening up. The fog is lifting. And in a way, the fog is also comforting. The unknown is not a threat. It is a promise. It is the promise that there is more to discover, more to understand, more to wonder at. The frontier will always be there, receding as we approach it, always offering new horizons. What feels fixed is often only familiar, and the frontier reminds us that the universe is far larger and stranger than any map we can draw. Let's take a moment to recap where we are. We have explored the possibility of Planet 9, a ghost world in the outer solar system that might explain the strange orbits of distant rocks. We have discussed the search for biosignatures in the atmospheres of exoplanets, using the James Webb Space Telescope to read the chemical fingerprints of distant worlds. We have contemplated rogue planets, worlds without stars, drifting in darkness, possibly harboring life in subsurface oceans. And we have stood at the edge of the great question: are we alone? The frontier is alive with possibilities, and we are fortunate to live in a time when these questions can be asked not just with wonder, but with data. The clock on the bedside table continues its rhythm. Tick, tock, tick, tock. Out there, in the dark, the search continues. Telescopes scan the sky. Algorithms sift through data. Astronomers submit proposals and wait for telescope time. The universe keeps its secrets, but slowly, patiently, we are learning to listen. A planet is both a thing and a question, and the questions we are asking now are the most profound we have ever asked. As we drift through these thoughts, consider your own place in this vastness. You are listening to this from somewhere on the surface of our own beautiful, round, orbital home. Maybe you are in a city where the streetlights outshine the stars. Maybe you are in the country where the Milky Way is a river of milk overhead. We are all passengers on the same ship. If you have enjoyed this journey through the dark, consider joining our quiet crew here at GravityWhisper. A simple click on the subscribe button helps us keep the signal strong. And I'm curious, where are you listening from tonight? And as you drift off, which planet in our solar system feels most mysterious to you? Is it the storms of Jupiter, the rings of Saturn, or the icy silence of Pluto? Leave a comment below. We read every one under the stars. Your thoughts are part of the signal we send back into the night. Now let us return to the room. Let us return to the bedside table. Listen to the clock again. Tick, tock, tick, tock. It hasn't changed. It has been marking time faithfully while we traveled billions of miles in our minds. The room is still quiet. The ground beneath you is still solid. But perhaps now you can feel the motion. You can feel the gentle rotation of the Earth carrying you toward the sunrise. You can feel the orbital drift carrying you around the sun. You can feel the sun drifting through the galaxy. We have asked, what is a planet? We found that it is a body that orbits the sun, has become round by its own gravity, and has cleared its path. We found that definitions change, but the worlds remain. We found that the universe is full of variety, from hot giants to cold drifts. We found that we are connected to these celestial bodies through the phone in our pocket and the calendar on our wall. The universe is calm, even when it is strange. The debates of astronomers do not disturb the orbit of Jupiter. The classification of Pluto does not stop its heart of nitrogen ice from beating. The names we give things are for us to help us understand. But the things themselves exist in a silence that is older than words. You can let go of the questions now. You can let go of the definitions. You are safe on this planet. It has cleared its neighborhood. It is round. It is orbiting faithfully. It protects you with its magnetic field and warms you with its atmosphere. It is a good ship. Rest now. The planets will still be there in the morning. They will continue their slow, majestic dance while you sleep. The universe is holding you. Good night from GravityWhisper.